There you go.
Molarity is moles of solute over liters of solution. What's the unit for molarity? Capital M, but there's another unit. Moles per liter. So molarity, or moles per liter, that's the unit. So if you know the acetic acid is 2 moles per liter, and you have 10 milliliters, right? So think of it this way. You have 2 moles per 1 liter. Let's multiply that by how many liters is 10 milliliters? 0.01. 0.01 liters. Liters cancel. So this is definitely the type of calculation you have to do on paper or in your head without a calculator on the AP test. They like to use 0.01, 0.001, 0.000. They like to use the number 1 with a bunch of zeros and decimals, and then they give you a whole number, and you just have to be able to do that in your head. So what's 2 times 0.01? 0.02, right? Yeah, that's not too bad. 0.02 moles. And you'll see as the year progresses and these decimals get a little bit bigger or smaller technically, you can always just say, okay, 2 times 1 is 2, but then I have to move it 2 decimal places, 1, 2, and that's another way to kind of think of it. 2 times 1 is 2, move it 2, that's 0.02. So however you want to, get comfortable with that, but that's something you should do in your head or on paper. Anyways, so that's how many moles, I'm just giving you a little help with this. That's how many moles of the acetic acid, the vinegar, is in each flask. But not all of it reacts in all of them. Sometimes it does, sometimes it doesn't. You have to figure that out. Yeah. All right. Okay, so we're good with limiting. All right. Now, I'm going to take that example we just did in our notes. So I'm just going to quick teach you this concept called reaction yield. It's pretty simple. It's almost like well, never mind. That doesn't make sense. Reaction yield. Another way to say this is percent yield. That's another way to say it. So there's always 2 ways to look at a chemical reaction. There's the paper version, like what should happen, and then what actually happens in lab, right? So we could do math. In fact, take the demo for example. If we were able to somehow mass, which we could have. I should have done that.
No.
We could have massed one of those flasks before I mixed them, and then after I mixed them, and you can figure out the mass of CO2. Right? You could actually figure that out. Assuming the balloon's airtight. It isn't, so maybe some of it got out, but yeah, I should have done that. So that's right. Anyways, there's always two parts to a reaction, right? There's the accepted and then the measured, right? The part you actually do. That's what this means. That's what this is. So let's take the example, and I'll just give you an example here. Let's take the one we just did. So the accepted value, here we go, write this down. Accepted value for the amount of NH3 produced. So I'm going back to the previous problem. Skylar, I forgot to record, sorry. The answer was what? How many grams of NH3 did we get? 28.39, right? Look back, 28, that's what I have. Yeah, so that was the accepted value. So it was 28.39 grams, okay? So on paper, in other words, I gave you 42 grams of N2, 5 grams of H2, and we did all that math, we did all the calculations. Then let's say we went back and we did it. We had nitrogen gas, hydrogen gas, and we actually reacted them to get ammonia. So let's say we did that, and we had a good way of measuring the mass of the ammonia. So again, let's say we did the lab. So the measured value for the amount of NH3 produced let's say we create 27.5 grams. I'm just making that up. So let's say we do the lab and we get 27.5 grams. I really wish I would have, because I would have been perfect if I masked it and then I could use the demo. That's okay. Maybe I'll recreate the 6th flask tomorrow or Monday, and we'll just, so I can relate this to like an actual example, and then we'll see. So we'll do the math and then we'll compare it. But what's the problem with that? If I recreate it, what's the problem with that? Yeah, so all the powder, some of the powder gets stuck in the balloon. I'll do, whatever. We'll do it and we'll just see how it turns out. But you can't really recreate exactly the same. It's really hard to do that. But that's okay. So, all I'm trying to explain here is that this is like the book value or the calculations on paper. All right? I mean, you've heard lots of times in your life, maybe you haven't, but people say, well, on paper, this should work out. Or on paper, this team should beat this team. Or on paper, and then in real life, it doesn't work out that way. Or you have a plan, even like, I don't know, you got a busy Saturday. You're like, I'm going to do this, 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 and this. And I'm like, yeah, it's going to be a good day. And then you get like 2 things done because something happens, right? Life happens. So, same thing in here. This is what should be produced, but you only get that. How would you find your percent yield? What do you think we do?
Measured over accepted 20 times 100.
That's it. Very good. Measured over accepted. So percent yield is measured over accepted times 100. Very good. So this would actually be a pretty good percent yield. Why don't you guys calculate it? What is this percent yield? What would this be? And this is it. I'm only giving this one example. We're moving on because it's not a hard concept. I just wanted to bring it up so that you know what that means. If it asks for percent yield, what does that mean? That's what it means. So when you calculate this, it's 90 something. So 27.5 over 28.39 times 100, and we get 96.8. 96.8%, which is real good. There was a lab in college, I forget now at this point what it was, but we were getting graded on our percent yield, and I got like a 5% yield or something. Yeah. Did I tell you guys about the crystal growing lab we did? Some classes I taught, I don't know. You got judged, you got graded on like how big your crystal was. I had like this, you need like a microscope to see my crystal. And I remember the girl next to me had like this pretty big crystal, and I was just like, so like such a doofus. I had trouble in lab sometimes. I did well in class, and I understood concepts, but in lab I would always make mistakes. So I share that because if it happens to you, it's okay. I'm still a chemistry teacher. That still worked out for me. You make mistakes. Some labs I did well, but anyways, back to this. You got it? Good. Moving on. All right. Next thing on the list here. All right. Before we get into, all right. So our next lab, it's actually pretty cool. We're gonna find the hardness of water.
What?
So do you know what I mean by hard water?
Yeah.
Do you know what 3 ions make water hard?
Sulfur.
No. No.
Iron.
Yeah. Calcium, iron, magnesium. So Mg plus 2, Fe plus 2, Ca plus 2, they make your water hard. Water softeners do ion exchange. So they take those calcium ions, iron ions, magnesium ions out of the water and then put other ions in there, like maybe sodium ions. I know it's not the same charge, but if you have enough of them, it works. Water softeners, anyone have one? No? Yeah? You have to get bags of salt to put in the water softener. I don't know if you do that or someone comes to your house and checks it and does that, your parents or whatever. Yeah, so we're going to test, that's the next lab, is we're going to come up with a method for calculating, okay, what is the concentration of these ions in the water? And I think this lab is one of the ones where you're coming up with your own procedure. We do that a lot. It's part of like the new AP curriculum where you have to kind of develop some things on your own. So we'll learn the process and then we'll do the lab. So don't worry. There's a little hand holding on this one. Little bit. Just maybe be like a finger. Okay. Now, before we get into that stuff, though, we got to do one more thing that's related to percents, moles, that we've been talking about. All right. All right. So, percent H2O in hydrates. Percent H2O in hydrates. This is another thing I wanted to talk about. So, where is my sample from? Hold on, I'm sorry. All right. Do you guys remember what a hydrate is? What's a hydrate? I'll give you a name. Magnesium sulfate heptahydrate. How would we write the formula? What's magnesium sulfate? Mg. Yeah. Mg plus 2, sulfate minus 2. You need to memorize those polyatomic ions. You really do. You really do. So I hope you know for tomorrow. So magnesium sulfate, and we put a dot. Hepta means 7. Hydrate. Find the percent water in that. Let's go. And then there's another problem I want to do with you, and I don't know where it is, so give me a second. Or while you're doing that, I'll find it. I think it might be in the book. You guys have your books with you? Oh, something to remind me after this, we got to talk about the problem set. So I'll forget. You guys ready? Yes, no, maybe? Another minute? What did we get? 51.2. Anybody else? How do we do that, Liz?
The grams of water over the total.
What's the total mass of everybody here?
246.
246. So you did 24 plus 32. Yep. Plus 64.
Yeah.
And then 7 times 18 is 126. So you did 126 plus 64 plus 32 plus 24 to get that?
Yeah.
Good. So percent water would be 126 over 246 times 100. And you said it's 50 what?
51.2.
There we go. That's how we do it. That's the Regents problem. Now it's gonna get real. Grab a book. I can't say stuff like that out loud. Anyone who talks like that takes himself serious.
Mine's in my locker. Can I go get it?
See if you can just grab one from the cabinet over there, where Luke is.
What?
Any left?
Yeah.
Yeah. All right, you're gonna go to page. I was gonna give it for homework, but we'll just do it right now. 115. All right, number 141. It's confusing. So I'll give you a little help. It says the formula of a hydrate of barium chloride is BaCl2.XH2O. If 1.936 grams of the compound produce 1.864 grams of anhydrous barium sulfate upon treatment with sulfuric acid, calculate the value of X. What does anhydrous mean? What's the prefix "and"? What do you think hydrous means? Water. Okay. What's anhydrous?
One water.
No water. An is like anti. So, or negative, like a negative prefix. So, I'm not using the right English terms there, but anhydrous means without water. That's what it means. So, if you have barium chloride with water, right, that's a hydrate. You treat it with sulfuric acid. All right, so really what's happening is you have BaCl2.XH2O. You treat it with H2SO, sulfuric acid is H2SO4. So these two react. Now you're going to get BaCl2. That's what it means. All right, there's might be other products, but I don't care about that. This is anhydrous because it lost all the water. So it told us
Should
that
it be BaSO4? Or where did you get H?
it says.
It says the anhydrous is BaSO4.
Yeah.
Oh, I'm sorry. Yeah. My, sorry. I wrote the wrong one. My fault. So yeah, you have BaSO4, which is anhydrous. Where'd all the water go?
Evaporate.
Yeah, evaporate. Okay. So if you react this with sulfuric acid, it reacts where it allows all the water to be released. Okay. So this has no water. Now it said the barium chloride is 1.936. So this whole thing is 1.936 grams. This compound, BaSO4, is 1.864 grams. Okay. Is there anything in common between this hydrate and this? Yeah, okay, the BA, good. So, what do we need to do? We need to figure out.
BA in that thingy, maybe. No. Okay.
Find BA in that thingy. I'm assuming you mean find BA in this
Yeah.
thingy. Okay. Remember, what did I say earlier today? With any type of problem involving reactions, stoichiometry, percents, grams, moles, particles, what do we always find first? Moles. So if we turn this to moles, how does that help at all? If we turn this to moles, how does that help at all?
They'll have the same percentages.
Maybe.
I give you
Can you turn this to moles?
the-
No, you don't know that, right?
If you turn up the mold, you can use the BA as a 4. And
He said the same percentages.
Oh.
I don't know if that helps.
yeah, really. Where'd CO2 go?
CO2.
CL.
Oh, who cares?
Who cares? It's part of the problem.
If you look at the previous example, magnesium sulfate heptahydrate, right? What's the mole ratio between the magnesium sulfate and the water?
1 to 7.
Okay. So that's where we're headed here, right? That's what we're trying to figure out. So if you have 1 mole of BaCl2, how many moles of water do we have? You know the mass of the whole thing. I'm being vague on purpose. I'm just trying to, Go ahead, talk to somebody near you. Come up with an idea. I'll give you a couple minutes. See what you think. We need to figure out moles of water. Is really what we need, right? That's what that essentially means. The mole ratio there.
Wouldn't you just find like the mass of the BaCl2, subtract it from the total mass, and then change that whatever's left over the moles with H2O?
Do it.
What?
I don't know.
Find the mass of BaCl2.
So you just convert that to moles? No, you just take that mass, subtract it from 1.936. But that's not gonna be the same.
Oh, take out problem set number 1. I keep forgetting to talk about that.
You just maybe lose my train of thought.
Sorry. All right, so I can't find it. All right, so problem set number 1. It says for the following 7 reactions that can occur in laboratory situations, show the balanced molecular formula for all reactants and products, then show the balanced ionic equation and net ionic. All right, I don't want ionic equations. I want net ionic, not ionic. So the reason I'm showing you this or talking about this is to make it clear. You must label solid liquid gas, assume reactants are ionized, separate piece of paper. Number 3 is tricky, it's not simple. Okay. All right, so what is the net ionic equation? Let me just show you quick. I know I kind of jumped right from this to that. I just don't want to forget to talk about this. So if you react, so that demo I do with the yellow precipitate every year, it's PbNO3 plus Ki yields PbI2 plus KNO3. So these two are aqueous. This is the yellow solid precipitate, and this is aqueous. So a net ionic equation means when you have a reaction, the ions that do not change are omitted. They're called spectator ions. So in this reaction, this is K plus and NO3 minus. This is K plus, this is NO3 minus. These two ions don't change. They just float around in the reaction. They don't do anything at all. So those are omitted. Those don't belong in what's called a net ionic. Net ionic shows only the reaction that actually happens. So it's PB plus 2 plus, I need 2 of those, 2I minus to balance out the 2, PB I2 solid. This was part of your summer work, but I'm just refreshing your memory. This is called a net ionic equation. You have your 2 ions here that produce a solid precipitate. So this is what your final answer would be. So if on number 1 on the problem set, I said, show the reaction for lead nitrate and lead 2 nitrate and potassium iodide, this is what you would write as your final answer. Oh, yeah, it's balanced. Okay, that's what a net ionic equation is. So that's what it means when it says write net ionic equation. So a lot of these might be a little confusing for you, but a lot of them are double replacement reactions. Almost all of them. Number 3 is a little different. It's similar to the one we did in the demo. It's sodium bicarbonate, which is baking soda with hydrochloric acid, so it's similar. Remember, CO2 is going to be produced. Okay, so separate paper, feel free to use the book, obviously the internet can help you. Alright, but just be careful with the internet, I'll give you a little wisdom here. Obviously you could probably just go on Google and type in literally all of these and get the answers, but that's really not going to help you do anything, that's not going to help you learn anything at all. So I really suggest not doing that. You know, try and do what you can, talk to each other, use the book. Last, resort, and talk to me. And then your last resort is the internet for a little help if you need it. All right. That's going to be due. When did I say that's due? Next Wednesday, right? Yeah. Did I write that up there yet? No. Okay. All right. So do we have any thoughts on this hydrate problem? I know we're running out of time. Didn't work. All right. Well, we'll pick up with this on Monday, but you do need to turn this into moles. So that's the first step. That's what we're going to do. And we'll pick up on Monday. So tomorrow, you got your quiz, you got a hand in your lab, and then you're going to have some book work. Same place, well, last year except you're up. You're now a different class, so you have to go to a different spot.